Week 12, Part 9, Lens Maker Equation. So let's just review how this works for mirrors. We already talked about this at least a little bit. If you look at a mirror like this, it pulls all the rays. This one, notice, is curled all the way around. And it focuses the rays to a point right there. But if I draw in the mirror, not doing a very good job, and indicate the focal point right here, and then take this all away, I think you can see that the center of curvature is out here somewhere. That's the center of curvature, and here's the focal length. And it sure looks like it's just a factor of 2. And in fact, that's true. That we learned that the focal length for a mirror is just 1/2 of the radius. So if this is the radius, and this is the focal length right here, the focal length is just 1/2 of the radius for a mirror. So that's all you need to know. If you know the radius, you can immediately figure out the focal length and vice versa. Lenses are just a little bit more complicated. So with a lens, you have 2 surfaces to worry about, not just one. And so let's say that we have a lens something like this one, and we're interested in trying to calculate what the focal length is, knowing the radius of curvature. Or the other way around, you want a certain focal length and you need to decide what radius of curvature would get you that. Well, there is an equation for that case, but it's a little bit tricky to use. So let's start defining some terms. Here is a picture of our lens, and out here would be the optical axis that we line the lens up on. And the lens has 2 surfaces, and they could have different radii of curvature. This particular one doesn't. They're the same, but they could, in principle, be different. And so we'll talk about the radius of curvature of one side. So over here is an R. It's really R1 over here. Let's put it over on that side. It's the first surface that the light encounters. Over here, we'll call that the radius. But it goes to a point over here. And then on the other surface, there will be another radius of curvature there. And that could be called R2, these 2 surfaces. And we will adopt the convention. This is a different convention than most books use, but I find it much easier and much more intuitive. We will say that the R's, the convention is the same for both R's. They are positive for convex and negative for concave surfaces. Convex surfaces we'll call positive, and concave surfaces will give the radius as being a negative number. If you adopt that convention, then the lens maker's formula is the following. 1/f is equal to n, that's the index of refraction of the glass, minus 1 times 1/r1 plus 1/r2. That's the whole formula right there. So let's do some examples just to be clear how to use this formula. So let's say you have a glass lens, and it is going to be plano convex. So it's got radii. The one side, the plano side, would be an infinite radius, and the other side is 12 centimeters. So a plano convex lens, that means that it's got a plane side and a convex side, like this. And so the plano side, the radius of that would be infinity, and the other side, 12 centimeters. What's the focal length of that? Can we figure it out from this information? Well, we can using this formula. So 1/f equals, if it's glass, we should be told what the index of refraction is. If we're not, we'll just use 1.5 for the index of the glass. minus 1, this is really the index of the air that the lens is sitting in. But we'll just call that 1. And then R1 is infinity, and then R2 is 12 centimeters. 1 over infinity is 0, essentially. You can ignore that term entirely. And so this 1 over f is just 0.5, that's 1/2 minus 1, times 1/12. And from that, we get a focal length of 24 centimeters. Okay, that's one example. Here's another quick one. What if we had a meniscus lens? And it had a convex, that a meniscus lens is one that has a concave and a convex side. So they're sort of like, they can be made either way, but we'll say something like that, sort of like a half moon or some weird figure like that. Then if the concave side has a radius of 32 and the convex side has a radius of 18. So out here we've got a radius of 18. Here we have a radius of 32. So then what we would say is 1 over f is this 1.5 minus 1 times. The first surface we come to is the more gently curved one. That's got the longer radius. And so that's 1 over 32. But watch out, that side is concave. So we must put a negative sign in right there. And the other side is convex. 18, not 8. And if you work this out, you'll get a focal length of about 82 centimeters. You could also ask, what's the power of one of these lenses? Well, the power would be 1 over 0.82. You have to convert to meters to get the power, and then that becomes 1.21 diopter. In a sense, this formula directly gives you the power, but watch out, if you've put centimeters in here, it won't give you the power in diopters. You have to change to meters if you want that to work.